Here's a really interesting starter all about black holes. And we have a black hole in space. It's known to have a mass of 8 times 10 to the 30 kilograms. And that's about 4 times the mass of our sun. At what radius from the black hole singularity is the orbital velocity equal to the speed of light? And this radius is known as the Schwarzschild radius. And it pretty much defines the what we call the event horizon of the black hole. It's kind of the radius where if you stay out of that radius, you might be able to escape from the black hole, but once you go inside that radius, you would have to exceed the speed of light to get out. And nothing can exceed the speed of light. So you are trapped and forever gone from the known universe once you fall into this within this radius. So here's what's given. We know that the mass of the, let me erase this. The mass of the singularity is given to be 8 times 10 to the 30 kilograms, and the orbital velocity is the speed of light itself. So how far from the center would that take place? So if you're watching this at home, pause it and work the problem out. But I'm going to work it right now. So let's solve it. So we have a very simple equation for orbital velocity. The orbital velocity is equal to the square root of the gravitational constant times the mass of the object that we're orbiting divided by the orbital radius of our orbit. That's from the center of the mass to where our object is located. Well, all of the mass is located at the center here, so so that's just r. So we want to take this and solve for r. So how do we do that? Well, we square both sides. And then we solve for r. The orbital velocity squared. And this little equation right here is the Schwarzschild radius equation. And it's really simple. Oh, one of the things you might know, we have a letter that represents the speed of light. You know what that letter is? Sometimes it's called Einstein's constant. Well, you've seen this equation before, right? E equals mc squared. Guess what that c is? That's the speed of light. So really I could go through, if I wanted to be really fancy here, I would say the Schwarzschild radius is equal to gm over the speed of light squared, because the speed of light is our orbital velocity. It doesn't matter what you call it, though. So now I'm going to plug all these in. G is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times the mass of my black hole, which was given to be 8 times 10 to the 30 kilograms. That's a lot of kilograms. Divided by c squared, and you've got to remember to square it, 3 times 10 to the 8 meters per second squared. So let's get the calculator out. And so I do it like this. Let's see if I can get it in the light. That doesn't really help. So we have 6.67. Use the EE button. Let's send to the negative 11 times 8 times 10 to the 30 equals, and we get a pretty big number, 5.336 times 10 to the 20, but then we have to divide by the square of the speed of light. So divided by 3 times 10 to the 8. I'm going to square that. And we get this value. 5,929. You round it off to the nearest meter. Now let's make sure that the units work out here. We have a Newton. A Newton is a kilogram meter per second squared. And so we've got a kilogram canceling, kilogram times kilogram, canceling the kilogram squared. And I've got a meter times a meter squared is a meter cubed, but that gets divided by a meter squared. So that just leaves a meter. And then I've got a per second squared on the bottom, and I got a per second squared from the Newton. So the only thing left is that meter. So, woohoo. So this is about 6,000 meters. And what is, so that's about, let's see, well, 5 kilometers is about 3 miles. So that's about a little over 3 miles, 3.5 miles or so. So it's not very big. Really, when you think about how big stars are and stuff, this radius is a few miles across. The diameter would be 10,000, well, actually about 12,000 meters, which is about 13 miles or so, 13, 14 miles across. Now, this is what's interesting about this is that if you were inside this event horizon, here you are, inside this radius, light from outside is being distorted by space. So you would see things, see light all concentrated and distorted from the outside world, but no light from you could get out. The only light that from you is light that can fall in towards the black hole. Now here's something really interesting. If you were exactly at the Schwarzschild radius, the light coming off, some of the light coming off of you could go into orbit around the singularity. So if you had really powerful binoculars, you would look in this direction and see the back of your own head. What? Yep. Space is being distorted so much. So, so that's how you solve these problems. And there's a lot going on here with time as well. They decided to call them black holes. This is a long time ago, like I think it was, the phrase was coined when they first started thinking about this stuff. But like in the 30s or something, I can't remember. But they also were thinking about calling them frozen stars. Because if you're an observer way out here, way far away from the black hole, but you're looking, you have a telescope and you're looking down at this, and then you have a partner or a friend who's falling into the black hole, when that black hole, oh shoot, okay. When that friend goes, as they approach this event horizon, it will seem as if they are slowing down. Time is being distorted as well as space. And in fact, if you're at the event horizon or in here, you, from an outside observer, it looks like they're going to stop. And from your point of view, if you're looking out at the universe, You know what it talked about in that video we just watched, how it would get infinitely bright? It would get infinitely bright because you're going to see the entire evolution of the universe go by. Because time, for them, is slowing down. So it's very, very, very weird stuff. The universe is incredibly strange when you deal with things that are either very, very, very small, like atoms and subatomic particles, or very, 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 very fast, like with special relativity, where length and time change, or in incredibly intense gravitational fields, where space and time themselves are being distorted. It's really cool. But it doesn't make common sense. When you learn about this stuff, don't try to make common sense out of it. Your brain is adapted for ordinary speeds at ordinary sizes, and so common sense doesn't work for this kind of stuff. So you have to kind of create models, make observations, make sure your models match the observations, and use those models to make predictions and test your predictions. And that's how we come up with these crazy ideas like general relativity and quantum mechanics. Here is something. There's a great big idea out there ready for one of you to discover. We have this theory of general relativity, which beautifully describes how gravity fields work in very intense gravity fields. And then we have quantum mechanics, which deals with the very, 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 very tiny. And it works beautifully in explaining how atoms and electrons and all these things work. This is why we have computers and stuff. It works great. But the predictions made by quantum mechanics and the predictions made by general relativity about what should happen at the singularity of a black hole do not match at all. They don't agree at all. Something is wrong with our understanding. If those two theories were perfect, they would predict the same behavior of nature at the same place under the same conditions, right? But they don't. So if one of you gets really, inspired and studies theoretical physics, and you want to have a unit named after you, or you want to be as famous as Einstein or Newton or something, figure out how to make quantum mechanics and general relativity agree, and you'll be famous. That is all.